All right, let's do 513. So that's the follow-up for this one, and I won't be as long-winded as I was before. So 513 is basically saying, here we give you a stalling torque applied at this point, the output of the shaft. It's 75 Newton meters, okay? And that basically, assume it's a different motor. It's stalling this gear train. It wants you to find the maximum shear stress in each shaft, okay? The output shaft has a little bigger diameter, 35 millimeters. The input shaft has a diameter of 30 millimeters, and that makes sense from the last problem. The torque on the output shaft is greater because of the gear reduction than on the input shaft, okay? All right, so once you do the previous problem, this is not so bad, right? From the prior problem, see if I can draw from the top view. Sometimes it's easier. Here's the motor. It drives a gear. It then drives a bigger gear. With an output. And there's some, well, on this one they put some bearings on the sides. The bearings don't do anything except just support the shaft positionally, but allow it to rotate. Here are the bearings. And here's the, okay? And I guess there's a bearing on that side too, right? Extend this out a little bit. Okay. So here on this one, they're applying the 75 Newton meters of torque. This guy has a diameter of 35 millimeters. And this one has a diameter of 30 millimeters. And it asks you to find tau max in both shafts. Okay? So we want to find tau max in both shafts. All right. Well, last time what we found out was the output torque is equal to the input torque multiplied by the radius ratio, or the ratio of the gear radii. And since the inner radius is, this is a smaller gear, this output shaft moves slower, which means the torque increases, okay? So that means this has to be outer over the inner. Or you can just memorize that equation, but I always forget, so I always do that little game to figure out whether it's outer over inner or inner over outer. And what we found was, well, we didn't find it, but this ratio here is, what are the numbers again? 125 over 50. Okay, so 125 over 50 is 2.5, I think, right? So it's 2.5 times the inner torque, the torque on the input shaft. I keep calling it inner, the input torque. Okay, so this is telling me that the torque on this shaft is 75 Newton meters, okay? And that's the torque applied on this. So it's, this section of shaft sees that torque of 75 Newton meters, all right? This section sees no torque, okay? So there's no shear on this section. That transmits the torque down to this section of this shaft, but the torque transmitted on this side is going to be reduced by 2.5. So I know this. So I know 75 Newton meters equals 2.5 times the input torque. So that means the torque on the input shaft is going to be 75 Newton meters over 2.5. Which is 30. Okay? So the torque is less, but the diameter is also less. So it's possible that the stress actually might be higher now. So we need to check the stress in both. Okay? Okay. So let's get J over C for both of them, because that's the geometric factor. Remember, we're going to use the stress, the maximum shear stress is the torque times the outer radius C over the polar moment J. So this is, again, the geometric stuff here. That depends upon geometry, so let's get that. So for the input shaft, that's, well, let's just write it in general. J is pi on 32 outer diameter to the fourth minus, oh, I'm sorry, this is solid, just diameter to the fourth divided by C. C is going to be 1/2 the diameter. So this just becomes pi d cubed over 16. So JC, or the shape factor, we usually call this the shape factor for torsion, for the input shaft is going to be pi on 16, the diameter cubed, that's 0.03 meters cubed. Okay, that comes out to be .6875 times 10 to the minus 6 meters cubed. For the output shaft, it's pi over 16.035 cubed. And that becomes 8.418 times 10 to the minus 3 meters cubed. Okay? So this is, right, torque over S. All right? Shape factor. All right, so now that I know that, I can compute the stresses in both of them. So the maximum stress on the input shaft is the torque on the input shaft divided by the shape factor of the input shaft. That's the J on C. So that becomes 30 Newton meters divided by 1.6875 times 10 to the minus 6 meters cubed. Then I'm going to get pascals. That becomes 17.8 megapascals. On the output shaft, that's going to be the torque in that shaft divided by its shape factor. The torque on the output shaft is the 75 Newton meters, and its shape factor is 8.418 times 10 to the minus 6 meters cubed. So that gives me 8.9 megapascals. So actually the stress on the input shaft is higher, even though the torque is less. And that's because the diameter is reduced. Okay?